Okay, I can see Tony is already logged in. So our last talk of the day, and it's a keynote presentation, is a personal view of history of confocal microscopy by Tony Wilson. And Tony is clearly the person who is most qualified to give a personal view because he's been there since the very beginning. As many of you will know, a lot of pioneering work in confocal microscopy has been carried out at his lab in Oxford University in the 80s and 90s. And I should also mention that Tony, together with Colin Shepherd, wrote a book with a name that escapes me at the moment. It's called Theory and Practice of Scanning Optical Microscopy, and it's considered a classic and standard reference in the subject. Unfortunately, it's been out of print for a very long time. So whoever can get hold of it, do that now.
Well, thank
you. Yes, Tony, you have a podium.
Thank you. So what I want to try and do in the next half hour is to try and explain how we got interested in what was at that time called scanning optical microscopy, and also to indicate that what people found interesting right at the start is perhaps not quite what people find interesting now. And I first ran a conference in The Hague in 1987, and it's marginally interesting to have a look what those talks were all about. And the other thing I want to emphasize as we go through this is that I started off believing I knew how the confocal microscope worked, and then pretty quickly realized that I didn't really, and it was much more subtle than I had first thought. So it's a purely personal view, and it's really trying to, if you like, sell you old microscopes for new, if you like, children's pantomimes. So you have to be able to at least do as well as people could in the past. And so here are some images I scanned from a book in the Oxford Library. Three-dimensional, very nicely produced bits of I don't quite know what, pollen grain, some sort of bug. And so the issue is, which instrument took these images? And the answer is this one. And these images were, of course, recorded by Robert Hooke in 1665 or thereabouts. Now, fairly clearly, this is not what he saw, but he was able to reconstruct from what he saw these really rather impressive images. So how did we get interested in Oxford? And I think the answer is probably this 1951 paper by J.Z. Young and Frank Roberts, where they started to speak about a thing called the flying spot microscope. And in the first paragraph, they make the remark that surprisingly, very little of the information obtained with microscopes has been quantitative. Most people are happy to sit at the screen and stare at the image, but rarely have people really tried to get anything quantitative out of the instrument. They also make the point that by imaging the whole thing in one go, if you like, imaging in parallel, that you lose the freedom to tune the resolution, to tune the imaging in a way which you would be able to do if you were to image sequentially, i.e. in a scanning approach. They also make the point that if you have a scanning approach from their flying spot microscope, that the quantum efficiency of the photo detector is much higher than a photographic plate, and hence one could, in principle, use a lower illumination intensity. Their point number 7 was one which got us particularly interested, where they say that the resolution in the ordinary microscope is, well, they use the word halation produced by the interference between neighboring particles, but they claim that in a scanning microscope, since only one resolvable region is illuminated at one go, one ought to be able to improve the spatial resolution. This possibility has not yet been systematically explored experimentally. It now has. So this is really what fired our imagination to start off with. This flying spot microscope, as Rimas indicated, I'm old, so I can remember when television screens had cathode ray tubes to display the image. And what a flying spot microscope is nothing more than a television screen with the electron beam scanning across the phosphor, producing a scanning spot of light, which is then relayed onto the specimen. It scans across the specimen, and you detect point by point, as indicated here, the light transmitted by the specimen, which you then display on a second screen, which is scanned in synchronism with the first. This flying spot microscope was built both in London and in UT Southwestern in the late 1950s. But of course, the problem is this spot is not particularly bright. But fortunately, then came along the laser, and that made a huge, big difference, clearly. So the original motivation was the observation that optics is pretty poor at seeing weak signals on a large background, whereas electronics is very good at seeing weak signals on a large background. So our original thought was, if we can get the signal in an electrical form, we can readily perform contrast enhancement. And here's a fairly early instance where we are just looking at the reflected light on the left-hand side from a rather badly cleaved optical fiber. And on the right-hand side, we are showing that there's a change of about 0.5% in reflectivity, which we can map into changes in refractive index. And so we could start off fairly early getting some meaningful numbers out of the instrument. So we had to do a scanning to get the electronic image. At that time, there were no CCDs or computers. The whole thing was done with analog electronics. And our motivation, really, to be honest, was the enhanced lateral resolution. We didn't really know much about optical sectioning then, and it was this enhanced resolution that was pushing us forward. I know some people have asked about the history of confocal, and I haven't done an exhaustive search, but the first reference I could find was to a paper in 1940 in German in an ophthalmology magazine. Then came a paper in Japanese, which I haven't read for the obvious reason I don't speak Japanese, in 1943. And if you look at the optical layout on the right-hand side, you can sort of see the confocal pinholes. From the same Japanese group in 1951 comes this instrument here. And if you look carefully at the light source in the bottom right hand, you can see a thing marked iris diaphragm. If you then follow the optical path through the objectives upwards, and then horizontally towards the photomultiplier tube, you can also see an iris diaphragm there. So this is clearly a confocal geometry. And then, of course, we all know the 1957 patent by Marvin Minsky. So that's a brief history. The first design that we had to find a way to scan. And we scanned using a mechanical scanner. Because there was no way to record the image, we had to have a long persistence television screen, and you could see the image build up as one scanned over the whole of the specimen. And this was the first scanner that we had. It had 2 vibrator-type voice coils scanning a support mechanism with flexible legs, as I show there. This didn't last more than a few days because the flexible legs broke fairly immediately and was replaced with a stretched piano wire system that I show in the image here. And also I show some fairly poor but still early images from the mid-1970s. The optical system you see in the photograph is absolutely awful, but it still worked up to a point. And we got a bit better, and here are some images of a fairly low resolution microcircuit, some resolution test specimen, and the ever-present diatom showing that it actually does work. Interestingly, one of the earlier things people were interested in was color confocal. And here's a conventional image and the confocal equivalent. The early commercial instruments, this is one from Oxford Optoelectronics, which we set up in 1982. This actually had stage scanning. Texas Instruments was the first customer. We then got into bed with a local company, Du Billier Scientific, which then turned into Laser Sharp and a slightly more professional looking thing. And the screens you see at the bottom of the image are the long persistent screen. This was only in 1984, and then Laser Sharp became Biorad, and the rest is more or less history. So the man behind the work in Oxford was a chap called Rudi Kompfner. He's the man who invented the traveling wave tube. And after his career in Bell Labs, he took 2 jobs, one where he spent the English winter in Stanford, where he worked on acoustic microscopy, and one where he spent the English summers in Oxford, where he started our work on optical microscopy. And here he is, and he was the chap who designed and drew this first scanning stage, which we then slightly modified into the form that you've seen. And here he is with 2 people. And I just draw this because one problem with scientists, no one knows what they look like. The man in the middle is Kompfner. The man at the left-hand side is a chap called John Pierce. And most people have probably never heard of John Pierce, but everyone knows one thing that he did. Bardeen, Brattain, and Shockley won the Nobel Prize for the invention of the transistor, but they didn't name the transistor. He did. So everyone knows his name for the device. No one knows who he is. Pretty much everyone listening to me knows the man on the right, but I'm going to leave it to you to see if you can remember or if you can recognize him. When Kompfner died, Pierce wrote his biography, and he spent a few sentences on his work in Oxford. And he said at the bottom here, he hoped to gain further advantage through observing harmonics of the illumination light. And indeed, that's what happened. Here's the scanning thing again. The thing in the top left is the photomultiplier tube, and indeed these were second harmonic generated images obtained in the late 1970s by Julian Ganaway in Oxford. And the laser was a homemade 1 watt CW neodymium YAG laser. We'd never be allowed to use that now. Amazing that we could do the thing then. A bit later on, we were able to do third harmonic and second harmonic, and here are third harmonic and second harmonic images focusing through a C. elegans nematode. Things have really improved rapidly. Now, 1987, we had this scan imaging technology SPIE meeting in The Hague, and it was very much the start of understanding how these things worked. But most of the talks were industrial. One here, new technique for spatially resolved minority carrier lifetime, scanning laser imaging of surface chemistry, scanning optical microscopy applied to fluorometry. Again, there were more things, applying the instrument to the measurement of submicron structures, real-time scanning by Gordon Kino from Stanford. And even as back as 1987, there was the inevitable lecture on super resolution. There was biology, of course, but it was very much in its infancy. So, optical sectioning is the important thing in the confocal, as we know, and that means you have to get the right detector. It has to be in the right place. It has to be of the right size. But the one question I want to speak about a bit this evening, or this afternoon, is, does this actually give the best optical sectioning in the easiest way? Well, we know that one way to look upon the optical sectioning is that the actual pinhole serves to obscure the light, and you only get a big signal from the light coming from the center. Absolutely true. And there are all kinds of formulae for what the strength of the optical sectioning is as a function of the pinhole size. You don't need to use a pinhole, and actually you can do, in some senses, better if you use a single mode optical fibre. You get exactly the same kind of optical sectioning. It gets more interesting, I'm not going to go into this in any great detail, if instead of using a fibre which supports just one mode, we have one which supports both the fundamental and the first order. Because if you do that, you find that you can form an image which is a combination, and you can separate out the various components of both a confocal image, a differential amplitude image, and a differential phase image, or any combination of the above. So one can actually be slightly more imaginative than a simple pinhole. But we all know what the problem is. The conventional microscope gives us this out of focus blur, which means we can't easily image specimens in 3 dimensions. So really the question is, we know that a microscope, if you like, is no good at this. Can we invent an optical system which will do what we want? So the idea is, can we form an optical system where the image on the right hand side is a scaled version in X, Y, and Z of the image on the left hand side? I'm not going to go into great detail on this, and the answer turns out to be you can, but the problem is you have to build a system such that the angle with which a ray leaves the specimen, gamma 1, equals the angle with which it arrives in the image, gamma 2. If you do that, you find that the magnification is just the ratio of the refractive indices, N1 to N2. That means in air, you can get a perfect image, just what you want, with a magnification of 1. And if you use oil immersion, it goes up to 1.5. No one's going to be very interested in that. So you have to basically eliminate the out of focus blur so that one can, in essence, concentrate on very good two-dimensional imaging and then build up a through focus series to get the 3D rendering indirectly. So what's wrong with the confocal microscope? Well, for our purposes, it has to use a laser. For our purposes, let's imagine, because it makes the story more interesting, that they don't image usually in real time. You've got to put the pinhole in the right place and you have to scan. So what would you like to do? Fairly obviously, you don't want a laser. You want it to be real time, easy to align, and no need to scan. Now, what have I just defined? I've defined a microscope with no laser, real time, no alignment, no scanning. That is what this thing does. So I've invented a microscope that Hooke had years and years and years ago, but it didn't have optical sectioning. So the question is, can we get optical sectioning into Hooke's old microscope? Now we know from our knowledge of confocal microscopes that the confocal microscope has a point illumination and a point detection, and it has optical sectioning. We know that the conventional microscope has uniform illumination, uniform detection, and does not have optical sectioning. So what do we do? Well, we ask Ernst Abbe. And we don't have to go very far because Abbe wrote lots and lots of letters, and here he is explaining his theory of the resolution of the microscope. This is in Abbe's own handwriting, and if you go to Jena, you can see a statue here on which he has his D equals lambda over 2n sine alpha resolution thing. But he basically said, look upon the specimen as a diffraction grating. Think in terms of spatial frequencies. So let me say what this optical sectioning is in exactly the same way that I've done here, but in terms of spatial frequencies. The frequency of the structure of the illumination in the conventional microscope is 0. The frequency of the structure of illumination from a pinhole, let's say, is many, huge numbers in the confocal. Frequency of the structure of the detection is 0 in conventional, many in confocal. Confocal has sectioning, conventional does not. So the idea is 0 spatial frequency doesn't give you sectioning, all spatial frequencies do. It turns out that in the confocal illumination results in an averaging over all spatial frequencies. I'm not going to go into the mathematics. So if it's an average, it can't be the best. Now, an appropriately chosen spatial frequency, therefore, must be better. So the approach is to use a single spatial frequency carrier to ensure good sectioning, and then find a way to demodulate, or to put it in English, to remove the carrier. So this is the whole idea of structured illumination. You have a structure to cause the optical sectioning to happen, and then you have a demodulation phase to remove the structure. And this can be done easily as an add-on to a conventional microscope. Let me try and explain. If I try to image this part of a transistor here, if I project a pattern, a grid line onto the specimen, you can only see the grid line where the microscope is in focus. So what you have to do is invent a way to get rid of the bits of the specimen where there are no grid lines, and then get rid of the grid lines. And so what you basically have is a background image which you aren't interested in, together with a sectioned image modulated by these fringes. And one way you can get rid of them is computationally. You take, for instance, 3 different images where you slightly move the grid between each of them, and you computationally work out what's happening. And all you need to modify the microscope here is to add in a paddle. Here is the OptiGrid paddle to the Illumination. And then you're able to turn conventional images like this into optically sectioned, crisper images like this one. You might think it's unnecessary to do the computation, and you have to take 3 images and you have to make sure they're the right 3. It turns out that instead of that, if you pass the composite image back through a reciprocal mask, exactly the same as the mask you used to illuminate, and you spin it, you, in essence, in a very hand-waving explanation, you perform synchronous demodulation, and you are able to extract the optically sectioned image. And if you do that, and if you get the frequency of the grid correctly, it's very light, efficient, and actually one can get enhanced optical sectioning. The blue line here is the ideal optimum spatial frequency for sectioning. The purple line is the ideal point scanning confocal, which of course doesn't exist. And the other one is the ideal slit detector. So you start off, you can get images like this as I focus through this specimen. They're optically sectioned, and you can add them all up to get an extended focus image. And as Pip was indicating earlier, these were taken with a light, with a candle, if you like, the ultimate laser-free confocal. So we started working on this, having had the idea. We then started to do some optical design. We then started to see how it might fit around a microscope, and a bit later on it looked a bit like this, and it now looks a bit like this. This is the Clarity, which Pip will speak about more tomorrow, and it's an add-on to a conventional microscope, and it, like all these other things, turns images looking like this into images looking like that. It can also get things moving quite quickly. So here is a zebrafish with its heart beating. Now, the other thing the Clarity can do, apart from the conventional, it can take the confocal. So what was being shown to start off with was the confocal image, and then switching to the conventional a bit later on. More of these videos, because they're quite pretty. This is a brassica thing. You can get these really rather nice 3-dimensional images, and more and more. I just show them because these instruments form images which look exactly like, if you like, a real confocal microscope, because it is a real confocal. It can be used in other applications. Here's the 3D Histech slide scanner, where the normal fluorescent image can be improved to making it confocal. I started off by saying one of the applications was metrology, and here it is in the guise of the Zeiss SmartProof 5. And here is a thing that is trying to be profiled. It's a dental implant, and the interest is in the angle of the implant, which is supposed to be 120 degrees. Pip mentioned the Unity, the laser-free confocal, so I shan't speak about that anymore, other than to say here is a scientist in a white coat using it, and the whole thing is controlled, as she said, from this tablet. So, new microscopes for all. You can do an enormous amount with Hooke's microscope. You can probably do a little bit more with either Clarity or Unity, but they both produce images which are substantially the same as you would get with a traditional confocal, but hopefully at a lower price, and I have no idea what the prices of these things are. And in this instance here, you just put in the specimen and press go. Okay, I think that's all I want to say, really.
Thank you, Tony. Thanks. Entertaining as always. We have one sort of quick question on our chat line. Jan Pechle is asking, can you give your personal perspective on Petran's and Hadravsky's work?
Yes.
Early work on a Nipkow disc confocal? Yes,
I actually had a lecture on this. I have nothing but the highest regard for Petran and Hadravsky. Actually, what Petran did was really quite remarkable. When he first built his microscope, the question is, what did he use for a light source? Because quite clearly there was no no laser or anything. And
a candle, perchance?
No, well, sort of. A rather well-known candle called the Moon, or rather called the Sun. He took the microscope up into the high Tatras mountains and used the Sun as the light source. But I've been very fortunate to know Moimir and Milan for the last, I don't know, 30 or more years. Milan, of course, died a few years ago, and I think their work, and particularly where they were doing their work, is extraordinarily impressive. Both, I might say, not physicists, but medical doctors.
Okay. Kirti Prakash is asking, why didn't confocal get a Nobel Prize?
Well, I wasn't on the committee, so I can't answer that.
He also says he heard that Nobel Committee didn't like outspoken Minsky. Didn't Minsky effectively drop this as soon as he invented?
Minsky, I don't think, I went to his house once, and I think he claimed to have built something which he couldn't find. I believe that to be true. But it wasn't what he was particularly interested in. Minsky certainly is outspoken, and he's not everyone's cup of tea. But I can't believe that was the reason.
Okay, I have a sort of question. I remember when I first came to this field, OBIC was still going strong, and it was regarded as a sort of a future of scanning optical microscopy. What became of OBIC?
I don't know. I think it was a very good technique. I mean, for people who don't know, it's the optical version of the electron microscope EBIC technique, where you scan an optical beam across a semiconductor, generates electron hole pairs which can probe various properties of the device. And in a way, it's superior to the electron beam because there's no electron beam damage. It didn't catch on in the way in which the acoustic microscope didn't catch on. I mean, really, all the optical microscope can do is measure refractive index. Well, frankly, who cares? The acoustic microscope, on the other hand, does measure serious material properties.
So we have a question here. So who was the person on the photograph?
Ah, Harry Nyquist.
Very good.
It's a great shame people aren't remembered in this way, I think.
So we have one more question here. Is it possible to identify who actually built the first scanning microscope with a galvo mirrors?
Whew. I don't know that. I can identify that we built things with galvo mirrors that didn't work, but that probably isn't the
Fred Brackenhoff?
Could be, but he was doing stage scanning like us, as was Finance at Emble. So it was probably only when it started to become commercial that people started to do beam scanning. I mean, to be honest, we did stage scanning because it made the optics easier. You know, to build a proper beam scanner. Oh, wait one moment. The other people who built beam scanners very early on was the Japanese company Lasertech. And they had a hybrid scheme. They had a mirror for scanning in the relatively slow frame direction, and they had an AOD for scanning in the line direction, and that was a real-time microscope. So that was, I'm going to guess that might have been the first commercial high-speed beam scanner. But I don't really know the answer.
Okay, we have a question here that I can probably answer. What is the SOM? Scanning optical microscope. It's one of the older ways of calling it, I guess.
Yes, you see, when we started, we always called it a scanning optical microscope because that was what, I mean, it was a flying spot microscope, and the word confocal didn't come until later. Who coined it for the first time, I don't know. It could have been Fred Brackenhoff, as someone suggests. I really do not know. I mean, it's a thing we in Oxford used, we came up with the confocal, if you like, because we like mathematics. And if you stick a pinhole in the equation, it becomes a delta function, and the integral is easy. So we actually had a thing called a type 1 microscope, which was the regular confocal, and a thing called a type 2, which was the scanning microscope with the pinhole, which of course is the confocal. But who came up with it, I don't honestly know.
I think you really need to look for a laser physicist here because of confocal resonators.
Well, this is the whole thing. If you know a confocal resonator, you wouldn't call it a confocal microscope, you call it a concentric microscope because it's not a confocal. But I think we're being a bit too anarchy about this. Oh, it could be Kjell Carlson, it could be Niels Aslund. I wouldn't know. They were amongst the earlier people, and Niels Aslund had a company, the name of which I can't remember, which was selling beam scanners early on. You could be right. I really do not know.
Okay, guys. So if there are no more questions, I think we'll probably draw a line here.
Okay.
Thank you, Tony. Thanks.
Okay,
thanks again for a very sort of
slightly more, not quite as smooth as it ought to have been.
No, thank you very much.
Smooth enough.
It was, I think there was something for everyone there, from all different countries involved in the development as well. It's great, really, really good. Even I understood it. Said something.
Okay, yeah.
But, I mean, thank you. Actually, I'd like to take this opportunity to say thank you to everybody today, both for attending and for the questions, but obviously, in particular, to all the speakers who've done a great job in preparing and done a brilliant job at speaking to the wall in their spare room and listening to the quiet feedback. And I think everybody, by the looks of it, agrees. It's been a great day. And I think we're probably all worn out now. So please come back tomorrow. Join us in the UK at 9 o'clock in the morning, UK time, for the next session, which is on, I think, image analysis and AI, followed by adaptive optics, I think. And hopefully we'll see you all again in the morning. And thank you once again, Tony, for a great talk. And
Thank you.
Really nice to see where everything came from. Thank you, everybody.